So now I want to explore partial derivatives a little bit more in depth. Like I want to look at them visually, what's going on, and I also want to make clearer that analogy to statistics that I mentioned with multiple regression. Just because I know some people in this course have already had some statistics classes where you've done multiple regression, so it might help to relate it to that, right? So, and if you've never done multiple regression, you can just kind of ignore this part if you don't find it helpful. But this is just one case where you kind of see it in action. So when we have a multiple regression, once we find our coefficient terms, the equation that we're looking at is y hat equals, maybe you have an intercept term, beta hat naught plus beta 1 hat x1 plus beta 2 hat x2. Okay. So this is, here we're treating y as a function of x1 and x2. Okay. So we never really use y as the, well, we do sometimes, but in the context of regression, we typically use y as the dependent variable, and then we have an indexed x terms for our data, our independent variables, right? So if we look at this, if we look at the partial derivative of y hat with respect to, say, x1, this part is just a constant, so that would be 0. Here, we would take the derivative of this, we would just get the coefficient in front of there, beta 1 hat. And then here, we're treating this as constant, so we get 0. So this tells us that beta 1 hat represents the amount that y hat changes with respect to x1. Okay. So basically exactly what we would expect. So this shows us that that same interpretation of multiple regression, where we're interpreting the coefficients as how much does x1, how much does y hat change as x1 changes while we hold the other ones constant, right? So same interpretation as the partial derivative because it is the partial derivative. And then if we did the partial derivative of y hat with respect to x2, we would get the beta 2 hat, as we would expect. Okay. So this tells us that as x2 changes, y hat is changing by this amount, assuming we're keeping the other things constant, because that's what the partial derivative is, right? It's telling us how much does x2 change, or how much does x2 change y hat as you hold x1 constant. Okay, so same interpretation because they are the same thing. So with that in mind, we will flip over to the graph. So I'm back to GeoGebra. I've been kind of switching between the two. I couldn't really figure out how to do this on the other one, though I'm sure it's possible. I just found it easier on here. So just to show how to use GeoGebra a little bit more. So we go to 3D calculator here. I don't remember if I used this one in this class or not. I know I used it in Math Tools 2 for the volume of revolutions, or solids of revolutions rather. But anyway, so here we can define a function. So let's say equals x squared plus y squared. Okay, so that very first function we looked at. So this is what it looks like here. You can kind of rotate it around, look at it from the top. So it has that same parabola shape as we saw before. We did look at this function before on the other calculator. So if we want to look at the derivative now, here we can use the derivative function. You can choose derivative function and then you specify the variables. So since we already defined f of xy, we can just write that in as our function. And then we can specify which variable we want to take the derivative of. And here we're going to say x. And it's equal to 2x, which we already saw. So this is the plane 2x. And we can see that the derivative now is represented by a plane instead of a tangent plane instead of a tangent line. But in general, that's just because this is a squared function, so it brings it down one, but it does have that same kind of idea where you can find the tangent plane at a point instead of just the tangent line. Okay. So we can see this is representing how much does f of xy change, so z change, as x changes and you hold y constant. Okay, so it's obviously a bit harder to interpret here, or kind of visualize. Even seeing it, it can be hard. So you can see it actually kind of intersects this I don't know what to call it. I think it's called a paraboloid. So then we can do the derivative with respect to y here. And we'll get the 2y for that one. So these are kind of overlaid on top of each other now. So I'll turn off the last one. And you can see how that one looks. And it's pretty much the same thing, just, you know, working with respect to the y-axis instead, as we would expect, right? So this one up here, this is the one with respect to x, and then this is the one with respect to y. Okay, so doing the same thing, just going in different directions, because one's with respect to x, one's with respect to the y-axis. Okay. So we can look at, I think I can just change this function here and it'll automatically change the other two. So we can go ahead and look at the other ones we did. So like x to the 8, e to the 3y, for example. And yep, the derivatives are automatically updated here. And they're both turned off right now, so we can just kind of see the function. So it's a, you know, kind of strange looking function compared to the stuff we've already seen. Like, I mean, most of these 3D shapes are going to be kind of weird in comparison. But you can kind of see the idea of this, where the e part is coming in, right? With that same kind of exponential graph shape taking place here. So with respect to x, okay, this is what it looks like. Okay, so you can see the part below here. So this is how much the output of the graph is changing with respect to x as we hold the y constant. And then if we do it, how much is y changing with respect, how much is y changing the graph as we hold x constant, this is what we get. Okay. So I think maybe this one's a little bit easier to interpret because it has that nice E shape that we come to expect, like that upwards curve, at least, you know, if we were to flip it this way or in different directions, you can kind of see that exponential shape here, which comes from the y part of it, since that's where the, you know, the y is, it's in the exponent of the E. So we would expect that to be how it's affecting the graph. Okay. And then just putting them both up. I don't know if I can change the color here. It would be nice if I could. But yeah, I'm not sure how to do that. All right, so let's look at some other ones. So the natural log of x to the 6th plus y to the 4th. Okay. So again, definitely a different looking function here. So all kind of centered around 0 here, right? You can see the derivatives here. Make sure these are what we got, and they are. So with respect to x, that's pretty drastic here. All right, this is a this function's kind of all over the place here. So this is telling us again how much the output is changing as x changes and y is held constant. Okay. And this is telling us the same thing for y. They actually look pretty similar. They're very similar functions, right? They're both rational functions. One just has y on top, one has x on top. Okay, so overlaying these on top of each other, like it can give you kind of an idea of how the graph is changing, but it's still just kind of very hard to interpret in 3 dimensions like this. It's hard enough just looking at a graph in 3 dimensions and trying to understand what's going on. So obviously it's going to be hard also just to look at the derivative stuff. So the stuff that we kind of emphasize, like curve sketching in single variable calculus, where you draw the curve, you draw the derivative of the curve, maybe the second derivative, and you see how they all relate. It's much harder to do in 3 dimensions just because the graphs are so much more complicated, right? So we're not going to emphasize anything like that here, but we're just kind of, it's nice that we have these tools where we can at least kind of take a look at them and see exactly what's going on here, even if it's hard to understand. Or maybe it's not hard to understand, I don't know. But for me, it always was. When I was going through Calculus 3, which is what this would be, we didn't really have any kind of, I'm sure these tools existed, but we never really used them or anything. We were just drawing pictures on the blackboard and kind of going off of that. So this is kind of a nicer thing to look at since we have this available. Okay, so last one that we did here, whoops. So this is the big long polynomial here. So we have x squared minus 3xy plus 2y squared minus 4x plus 5y minus 12. Okay. So I think this really, it would look more like a, it would be more kind of parabolic. I think maybe this just doesn't go down far enough to like kind of see the curves on it. But the partial derivatives, those would just be like planes, right? As we can see here, that they would just kind of be flat planes. They appear to be a little bit curved, a slight curve to them, right? So, but if we look at them from the side, right, they look pretty flat. So again, this one, or I'm sorry, I have this backwards, don't I? The red part is the derivative. The blue part is, I thought I had them both active, but yeah, that makes more sense. Now, the red part is perfectly flat. Okay, so that's why I was just confused about why the derivative, which is a plane, was curved. But yeah, we can see the red part is pretty flat. It's hard to get it so that we can see it as a straight line here, but you can kind of see that here. And yeah, we do see the kind of parabolic nature of the rest of it. This actually would be kind of more hyperbolic, which means you kind of have like a hyperbola is kind of like two parabolas like facing away from each other. So they have like their, what's it called? Their vertices like next to each other, but then they're facing away from each other. So you can kind of see that idea here. Again, it's kind of hard to tell just because I think just because they're kind of so big, but their vertices would kind of be like around here, and then they're kind of curving outwards from there, right? But then their derivative is just a plane. So this is how much the blue ones are changing with respect to x as y is held constant. Okay, and then same idea with this one. It's just basically very similar, just going in the other direction here.